No dream is too big and no background is too small. I'm here with Dr. Karan Jani, who came from a small school in India without any science lab and who has been one of the leading astrophysicists who was a crucial part of this team, LIGO, that discovered the gravitational wave in 2015. Dr. Jani is a professor at Vanderbilt University and is also leading the team, Leela, that aims to start this observatory in Moon to discover gravitational wave. And my favorite part about Dr. Jani is that he shared the stage with Shah Rukh Khan on this Tech Talk. Welcome, Dr. Jani.
Well, thank you very much. I'm very excited to be part of this new podcast.
Thank you so much for being here. First question, you study gravity, you study black holes, and there are so many interpretations of gravity. So what exactly is gravity personally for you?
I see gravity as a foundational element of this universe. If we did not have any stars, planets, anything that we would generally associate with the universe still has what we call space time. And space time, as we have understood since Albert Einstein's famous general theory of relativity, that the bending of the space time is what we now understand as gravity. So the very existence of us and gravity is sort of very existential to me. I think it's a link to some sort of a foundational idea that the universe was built upon.
Thank you so much. There has been some substantial improvement in our understanding of gravity, and starting from the Newtonian explanation to the explanation of the general relativity by Einstein. Do you think there are more upcoming theories that can answer stuff like singularity and infinity? Because as far as I understand, our understanding of black holes and the mathematics that we have so far kind of breaks down like when we have singularity and like black holes.
No, the beauty of general theory of relativity is that we almost by design we know its limitations. So while the theory does give us things such as singularities, whether the singularities at the Big Bang, whether the singularities at the stage of black hole, or whether the very concept of black hole itself, all of this are very classical concepts that require quantum physics as a treatment to understand. So, by definition, for singularity, it means something is, all the mass of the black hole is crunched at singularity. The singularity does not have a radius, which means at some point quantum physics should be important in considering what is singularity. General theory of relativity is not consistent with quantum physics. So we do know where the theory breaks down. It is very rare, in sort of a modern scientific sense, for a theory to be so remarkable, yet you know where its limitations are. So the future theories of general relativity or beyond in gravity, we kind of know where we would see the deviations. It's a matter of rather observations. Can the observations find that guidance for us of where a next theory happens?
There are also these ideas of how you can combine gravity with quantum mechanics, or like some very advanced theories that can explain all the fundamental forces together. Do you have any opinion about it?
No, I'm very agnostic actually. I think I always, as a physicist or astrophysicist, I take observation as my guiding force. And I am of the strong opinion that the observations would tell us where general theory of relativity needs to go next up in its current avatar. Like, what is the next theory of gravity that would come out of it? I don't think that an existing theory necessarily has to be the right theory where observation should lead, but it's the rather opposite way. If the observations tell us that, yes, the quantum nature of gravity is more consistent with an observation of a theory X or theory Y, then yeah, we will pick one of those. But I don't have any favorites.
Or do you think it might be like a situation where we go back to the starting of like our origin of the entire explanation of the fundamental forces itself and start from the grassroots level and completely change the idea of how we have defined everything until now? because there are other things like dark energy, and then there are so many other concepts in physics that have to like come in together, and everything has to make sense together.
Yeah.
So do you think there might be a reason we have to go back and start from the scratch?
Yeah. That's a good hypothesis, right? Will are our existing theories completely not suitable with the framework of the universe? I don't have such a radical perspective. I mean, there are few things there are two, I think, sort of moments as a scientist you feel very special. One is when you understand a knowledge which is near permanent, and the second is when you are able to contribute to a knowledge which is essentially near permanent. So, as a current scientist, what are the things that I have at least had the privilege to learn that I consider as a near permanent knowledge? One of them is the age of the universe.
Mhm.
The fact that we know the age of the universe now to like three significant digits is a very powerful testimony of everything else in physics that is has to work out in consistency. The quantum physics has to work out, the general relativity, the thermodynamical aspects of it, the nuclear physics of it. All of those theory, up to some approximation, is giving us a consistent picture of the universe. And that idea that even 500 years from now, I don't think that advanced species, or even human species, studying universe in either from Mars or from Earth or from Moon, will debate the fact that the age of the universe is not 13.8 billion years. We are very close to that answer. That further then tells, I mean, the age of the universe right after that is where we observe the cosmic microwave background. The cosmic microwave background is one of the first hints we have of dark energy and dark matter. In the early universe, in the later universe, we have many other links like the ones you mentioned. The motion of stars around our own galactic center means there is dark matter bulge. The expansion acceleration of the universe in the nearby universe tell us there is dark energy. But even at the cosmic microwave background, we know they do exist. And so I don't think that we need to do a revision completely, but it is nonetheless going to be a very, like, it is going to be a paradigm shift in the same way Newtonian physics to general theory of relativity was, or from the Maxwellian
Mhm.
electrodynamics, the Heisenberg quantum or Dirac quantum electrodynamics looks like.
That's a really thorough and concrete way of seeing things. And there are people who always ask these really fun questions like, can we live inside a black hole, or can we be physically present inside a black hole? And there are so many of these hypothetical ideas that you cannot directly prove, but there are mathematical constructs you can always put out there, and that might correlate to the physical reality, or that
Hmm.
might actually like provide a possibility of the physical reality. And one one example like I remember was this 1935 Einstein-Rosen paper that came forward with this whole idea of wormholes. And
Mhm.
that's when like all the people in Hollywood, like Hollywood mostly, like they started with this idea of like space time, like time travel and so on, so many other like fascinating topics. So how important do you think it is to be very skeptic about like these mathematical constructs that can give rise to all these fascinating ideas, but they might not be the actual reality?
Hmm. Yeah, it's a very deep question here, right? That do we invent mathematics, or are we discovering mathematics?
Yeah, yeah.
And does every mathematical construct should translate into a physical reality?
Mhm.
The answer is very different based on different disciplines of math and overlapping physics we see. For the longest time, people were not convinced that imaginary numbers can be real. I mean, by real, I mean in the physical reality, it can be represented, and that's why they were called imaginary numbers. What does a square root of a negative number mean? What is an area of a negative number? These are very difficult questions for human languages to understand. But in the language of mathematics, these are completely perfect questions.
Mhm.
If I want to take a square root of negative number, I mean, there are whole series of iterations that I can do to get the right answer. In that sense, though, what is surprising is the waves that we see, all forms of waves, are represented by imaginary numbers. Now, a physical reality is represented by something that cannot be defined in human language, but mathematically it is a very consistent model. And so there is always this thing that if you take humans out of the equations, the mathematics is still the language of the universe. We were not, even if humans were never on Earth or in the universe, the value of pi is still the value of pi.
Yeah.
We are here as an observant of that value. We have understood how that value is reached. Now then comes like, how far does this go that the universe always has a one-to-one map with a mathematical reality? Wormholes is one such example where, under the construct of Einstein's general theory of relativity, wormholes make sense. Wormholes make sense the same way singularity makes sense. Yes, mathematically they are there. Does a physical reality have to obey it? And that's when the answer comes slightly no for singularity, because it's absolutely missing quantum physics. And that's the sort of same things can happen for wormholes as well. That are we missing out on a physics because of which this phenomena is seen? Not very different actually what happened in the Newtonian time. So during Newton's time, we could not compute the orbit of Mercury with the Newton's equations, and the hypothesis was there is a planet called Vulcan
Mhm.
out above between Mercury and Sun. That's where the Star Trek reference comes in for the planet Vulcan. But now we understand that no, there is no planet Vulcan. And the theory is also not wrong. It's just the theory is not accurate at relativistic limit, which happens at Mercury's perihelion around the sun, and that's when you need the general relativity corrections. So the math of general relativity now is what we consider the accurate math. Is the general relativity math for wormhole as accurate in that sense? And I don't know. I don't think that it can be put in the same category.
Wow. That totally makes sense. For someone who does not have that much of physics background, how would you explain a black hole without any math at all?
There are two ways to understand black hole. I think one is just the word itself, which says that can there be an object so dense from which even light cannot escape? And that's an idea that has been around predating Einstein, predating the word black hole itself. It used to be called dead stars.
Mhm.
That can a star be, so massive that the escape velocity of light is greater than the speed of light. Um, Escape velocity, sorry, is greater than speed of light, and the change here happens in the context of black hole that we currently understand in Einstein's theory of relativity is that the mass of the black hole is not in the event horizon. Event horizon is still the radius from which light cannot escape, but that is not where the mass is. The mass is at the singularity. So you could be well inside the event horizon, but it's still a singularity at which all the mass is concentrated. And once we enter a black hole, we don't know of any way that we can come out from it, right? It is a black hole for all observers. So no observer would deny that they are not looking at a black hole, which is strange because relativity impacts both the length and time contraction. So the very concept of escape velocity should have been observer dependent.
Mhm.
However, light is the only thing that all observers agree on the speed of light. That is why a black hole remains a black hole for every observer.
Wow.
right? And that concept would not have happened. It's hard to say it in words though, because the word black hole is not the right word to express this. What we are seeing is a matrix with a marginally trapped surface, or a trapped surface. Trapped surfaces are one light, there is no path for, let's say, light to escape. We are not looking at the word black hole is a very recent. I think it comes actually from a reference the British historians had for a war in Kolkata, where they use it was the black hole of Calcutta, and that is where the word black hole comes in. It's not a physics word; it's just what we call colloquially.
Mm. I have seen this movie Interstellar, and so many of you have also seen this movie. Have you seen this movie, by the
Yes,
way?
it
Yeah.
is written by my one of my academic grandfathers, Kip Thorne.
Krypton. Yeah. What is your personal opinion about the physics behind the movie?
Oh yeah, no, it's a very great story. I think because from what I've heard is that Kip really wanted to make sure that the physics of it is as accurate as possible, and the of course there are some artistic freedom here and there, but the it is the best movie to explain someone what is relativity, both relativity in time,
Uh-huh.
the concepts of, like, wormholes, black holes, um, interstellar travel that could happen because of it. It's bearing the fact that when they enter black hole, I think everything else is very consistent.
Mm. Yeah, I saw this paper about the mathematics behind the movie, and that was really fascinating to see. And even the picture itself, the
Yeah,
picture of the black hole. When I saw the actual picture of the black hole released, it was like 2019, right? When it was released in 2019, I was really shocked, and I think that was when I was in high school, and all these really fascinating things are happening in the physics domain, and I was like, oh, I want to be a physics major. um, yeah, going back to the background and the starting days, um, how would you see yourself growing up in India and like coming up all the way up to here, being one of the leading astrophysicists in the field and making up your name in the field and leading all these really cool projects?
Hmm. No, it's a matter of privilege. I think with me, I carry s- some of my, I mean, my roots are very much active. I am I'm the way I do science is because of the way that I've come from. And I'm privileged that I've got opportunity to work on very exciting frontiers in our field with mentors who have taught me how to think as a scientist, what are the questions you should be asking, how you answer them. So a lot of training I've got from some of the leading names in our field itself. um, and I also am aware of the fact that the place that we come from do not have so many scientists, and so as a scientist, we have a certain duty towards society to both educate them about the science we do, and also guide them in terms of becoming more active in STEM fields. This is something that I absolutely enjoy. I love speaking with especially high school students who are very keen, and they have questions, and it's only a matter of getting in the right track, because once you're on that track, then a lot of things happen to you in really automation, right? I mean,
Mhm.
you take courses, you meet with professors, you get into research, you write papers, you go to you continue in your field, you present, etc.
During your early days, was there anyone who was really influential to you becoming a physicist?
Yeah. No, I mean, I didn't grow up in, I mean, I never saw any scientists growing up. Like, I did not know what a scientist is, like what do they do. There is no reference point we had. um, I had two early inspirations. One was when I was in high school, or slightly before high school. The president of India at the time was a scientist, Dr. Abdul
Abdul
Kalam.
Kalam, yeah.
And Dr. Kalam wrote, very nice books that were accessible for students like me who didn't really have, much other sources to be inspired of. We have, I mean, it's a joke, but it's true. I mean, most things we did was we talked about cricket, we played cricket, we watched Bollywood movies, and that is how much of our conversations were. And here was our president who gave, like what it means to be a rocket scientist, what it means to be an aerospace engineer. It really brought in like a new narrative that, wow, there is, all these big stars in cricket and films are there, but then there is a scientist who's a much bigger star. I was very inspired by Dr. Kalam. And when I finished my high school and I found a used copy of, from a book street vendor, I got a used copy of Hawking's Brief History of Time. And that was the first book I read cover to cover in life. Like I had never read, like other than textbooks that the government school has, you never read like any book cover to cover. And I thought I was just completely blown up, but I never felt this way. It's almost like, your spiritual awakening.
Mm-hmm.
Like every page after page, that the way he describes it. And there's so many things I didn't understand in the book at the time, but I was completely blown, like after reading that book. And then I decided, like, if because I didn't have any life plan, I didn't want to become an engineer. I wasn't smart enough to become a doctor or other things. I didn't really have any goal up to I was like 18, 19. And after reading that book, I was like, if I have to spend some time doing a thing in this life, then I want to study black holes. Like that, I was become very clear. Like one thing, if I want to do, I will study black holes. And I think since finishing up that book and till today, I've just never stopped doing that.
Wow. Did you have any inspiration, like, Einstein or Newton or any Western physicist?
I mean, they all were so far from the milieu that I was growing up. I just didn't see that anyone who's in my
Mm-hmm.
environment would ever become in
Mm-hmm.
that sort of race, right? So it was very hard to be inspired. I mean, you're of course, you have this sort of a respect for this, like these geniuses who have contributed to the world, but I just couldn't connect with them.
Mm-hmm.
I think the first such famous figure that I could connect myself in some very small capacity, of course, but was Subramaniam Chandrasekhar, which we fondly call Chandra, who won the 1983 Nobel Prize in Physics, the first person to win, I think, Nobel Prize in astrophysics, but clearly the last South Asian person to win Nobel Prize. Um, and Chandra's contribution to our understanding of the universe, I think, is at par with Albert Einstein. Chandra has told, I mean, the very idea of stellar evolution, what happens when a star dies, why it becomes a black hole. Because a lot of those foundational work comes from Chandra. Um, and he had a fair share of struggles to reach in his life where he is. There's a very famous controversy that happened when he was a grad student. He showed this result to his then advisor, who was a very famous astronomer, um, Arthur Eddington.
Mm-hmm.
And Eddington absolutely mocked him and made, and this is crazy. There is no way you can combine quantum physics and general relativity. And now, as we understand, that Chandra was always right.
Mm-hmm.
Um, and I think his life serves as a good testimony of how long the journey as an astrophysicist or a physicist is. You cannot be relying on validation. It's not like playing IPL that one match you score century and that's like you get this kind of, I don't know, this is a very long haul. Chandra did at 19 the calculation for which he got Nobel Prize in his 70s.
Wow.
Yes.
But he did turn out to be like the result he got was like not accurate or.
I mean, it wasn't something that we would consider today as a great result, but it's also the understanding of data analysis at the time.
Mm-hmm.
Systematics was very different, how they approached it. But Addington was notoriously arrogant, in the sense that some reporter, I believe, had asked him that is it true that only three people in the world can understand general relativity? And his response was, I only know two. which was him and Einstein. I was like, who's this third person?
Yeah, there are obviously people, especially around those golden era when physicists were celebrated like
Hmm.
rock stars. And I also saw your video on your TikTok when you were introduced by Shah Rukh Khan. So how was that experience?
Oh, so,
I'm
uh,
a big fan of Shah Rukh Khan, by the way.
who's not, right? Who's not? No, I'm. Yeah, it was very surreal. I think getting to speak about science, popular black hole, spoke about the discovery of gravitational waves that my team had done, that the fact that India is building a LIGO detector, and to say that A in Hindi,
Yeah.
which I think is important to do science in regional languages other than English, so that more people are excited and learn about it. And then to do with someone who's like, essentially like an iconic figure, um, it gives a validation to both I mean, to the stage that I'm saying, right? I mean, I could have said it at any other stage, it would have been the same. But when you share a stage with someone and that person is like so iconic and asks you about your science, it feels very great. And B, it also takes the message further. It amplifies it in a way that a scientist alone speaking will not.
I since physics is way more based on the Western culture itself, did you find any difficulty in translating the same
Yeah,
message in Hindi? Like, 'cause there are some words
yeah,
that might not even exist out
that is
there.
that is true. I mean, it's hard for me to do because I didn't have such strong English education in high school. I mean, I still keep telling, and this is true. I mean, I do physics in Gujarati. Like that is my native language, and that is how I've learned to do math. That is how I learned to think about physics. It's not, yes, I will still write equations in English, but the cognitive logic is happening
Mm.
in my mother tongue.
That's how I feel sometimes too.
Hmm. And there are terms which, I mean, it's not that the word gravitational waves in Hindi would be Gurutvakarshan Tarang.
Yeah.
I mean, that's not how we would want to explain, because gravitational waves is rather easier to explain in English that way. A black hole, you just have to call it a black hole in Hindi, Gujarati, and Nepali, whichever language one is speaking in. But the thinking of how your brain is doing it happens to me
Mm.
at least in my mother tongue.
Talking about, there are like initiatives in India, and India can be the frontier in all these scientific discoveries, mostly like revolving around the lab India is trying to
Yeah,
develop. What do you think is the status of the entire mm, LIGO lab in India?
yeah. I mean, this is a very high level government project, which has a lot of institutions attached. Um, it's definitely um, very noteworthy that India is investing in a field which is rather new field, right? Gravitational waves. I mean, it's been around, but it's only after the discovery of gravitational waves in 2016 when we announced it is that really the field took off.
Mm.
And now India is one of the leading countries where the gravitational wave research happens. A lot of produces great amount of PhD students. My own postdoctoral fellows, have been sort of inspired in their journeys from the fact that LIGO is happening in India. I think it's a all in all very positive, not just for India alone, but I would say for that region to have a science which is a very inspiring science that many in that region can connect with. The same way like how a gravitational wave detector elsewhere has, it's a global effort. Many countries are involved with it,
Mhm.
and they come and work at the LIGO detectors in the US. They work at the Virgo detectors in Italy. That's the kind of impact this will have.
Talking about your experience at LIGO, I know you were a crucial part of the team. How was your, not day-to-day work, but like how was your work like being a part of the team?
A lot of telecons. This is a collaboration effort. So there are many scientists that we all are interacting and trying to make sure our results are consistent, the review is right. One of the um, beauties of that discovery is, the amount of checks and balances that had happened before the gravitational wave discovery is just remarkable. When I teach the graduate course, I emphasize on so many other ways that, like ways that we vet whether a signal is real or not. And especially when you had to wait 100 years to have a discovery of this degree. So yeah, I mean, it is a, it takes a whole village to discover gravitational waves. So right now, let's say two of my graduate students are at the LIGO facilities. They work at the facility, and then one my other student right now here works on the data that already comes from the site, and then another student works on the astrophysics modeling of it. So it's a lot of moving pieces, and the fact that all of them line up is the beauty of modern scientific collaborations.
This shift of scientific discoveries have been more towards like all these large projects in the last couple of decades as compared to what it was during the golden era,
Mm-hmm.
when just like one scientist will just work on their lab or just think with paper and pen. So how do you see the future of science, mostly with like all the new technologies with
Yeah.
AI and mostly like data driven process? How do you see science and physics in general?
Yeah. So two parts. I think one is the large collaboration aspect. The fundamental physics projects are problems that are in front of us are very grand. They are no longer in the era where a lone genius can come and solve them. And that myth of lone genius needs to be busted, because we don't want new generation of students joining our field with that kind of an idea. Instead, what we are seeing is a collaborative research where several different expertise are brought in together: experimental side, data analysis side, theory side, astrophysically side, engineering aspect. All those things comes together, and all other experts in their each domain contribute, so that we now have an understanding of, how do we solve things like dark energy, how do we solve dark matter, the grand problems in our field. So I firstly think that the era of pen and paper science is not over, but definitely the era of one alone person going to work and solve, that absolutely has to be busted. There is no single person who will change physics now. That era is over. That kind of problems are over. The part of AI though is very interesting. We clearly are at a frontier to ask is, can discoveries be driven by AI? Can artificial intelligence models do fundamental physics breakthroughs? In present day, the answer is no. However, we have seen fields such as in protein folding, for example, which was awarded the 2024 Nobel Prize in Chemistry, which was driven by AI modeling that allowed us to understand protein shapes, which was not known conventionally. What is the equivalent of that for physics? Maybe if we start discovering gravitational waves from objects that are not really black holes, we don't have the mathematics of it. And if the AI tools can help us find symbolic relation of what beyond general theory of relativity is the first order correction turn where the signals are coherent. That is a discovery space I feel is going to come in maybe in 10 years.
Wow. Talking about the Vanderbilt Lunar Lab Initiative, can you explain more about the project itself
Yeah.
and the goal and the overall ambition behind it?
Yeah. Yeah. See, to me, one thing that I want to do within my lifetime is understand the quantum nature of gravity from an observational perspective, which means we have to build experiments that are ultra precise, that cannot be done on Earth just because the Earth has so many other sources of noise that impacts our measurements. And we also know this kind of experiments are very hard to do in deep space with current technology, which then brought me to this idea that, oh, why not do it on the moon? So in 2020, I published this first paper saying that gravitational waves on the moon has a unique observation space that cannot be achieved by anywhere else.
What do you
Um,
mean by that?
so there are frequencies of gravitational waves that we see on LIGO. We cannot see lower frequencies because the humming of Earth from seismic activity is already much stronger. And then we have space missions like LISA that would see much lower frequencies, but then they don't have the right sensitivity and they come from sources which don't really allow us to test such kind of theories. In between was this sort of a missing space in the gravitational wave spectrum where the moon is particularly good at. And it was known for a while. In fact, the Apollo 17, which is the last time humans went to the moon, carried a gravitational wave probe with them. Um, and apparently, it had a manufacturing defect and it didn't really work out the way it was expected. And after that, humans never went back to the moon. So there is a discovery space. Now, when we started, it felt like, wow, this is like a science fiction. Like, can you build a gravitational experiment on the moon? Because they are such complex experimental technology. It takes a while to make them happen. And so we started collaborating with all the experts. Vanderbilt had like a great set of experts in the Institute of Space Defense Electronics, radiation hardening, um, um, essentially like control feedback for running things robotically, etc. So we all got collectively together, and which is what the Vanderbilt Lunar Labs initiative is. But the idea doesn't rest there. While we want to discover gravitational waves from the moon and make this experiment happen, this is also an opportunity to train next generation students on how can they be part of the workforce for space exploration, for lunar exploration. We have now these great companies that are coming in. You have Blue Origin, SpaceX, Intuitive, all these new companies that are trying to build technologies for space and lunar exploration, multiplanetary species. How do we train the workforce for that? The same way the workforce trained, let's say, 2 decades ago for the IT revolution. And that's the other education aspect of lunar labs.
There are these education aspects, but then there are also these other aspects and constraints like financial constraints. And it seems like it's going to be a really long project with a lot of financial requirements. And how do you see the vision?
Yeah. But I don't see, one has to always look at why can you do chat GPT today, but you could not do it 10 years ago?
Mm.
Is that the cost per user to do it? Or is it the fact that the overall computing has become cheaper?
Mm.
So now you can have series of GPUs doing that work for you, right? Because the algorithms, to a great extent, not the attention booster, but several machine learning algorithms have been around for a while. So the answer is not that what your specific project cost you, but how is the ecosystem evolving in that direction? Right now, we have commercial companies that have just a couple of years old can land their own lander on the moon. The total cost per kilogram to land something on the moon is the orders of magnitude cheaper than it was during the Apollo era. And so then the question comes is, how much mass do you need to make a gravitational wave detector on the moon? Our current estimate is somewhere in the ballpark of a few hundred kilograms, or like 100 kilograms or so. So if it's 100 kilogram or so, that is in the current budget would be 1/100th the cost of James Webb Space Telescope, or 1,000th the cost of James Webb Space Telescope. Now then the question is it worth doing?
Mm.
Right? So one has to, well, if you had asked me the same questions in 2015, then yeah, the answer was it was very expensive. But in 2025, the answer is very different. In 2035, it will be even different. So it really, the science, I think the scientist has to learn what kind of problems they can solve based on where rest of the civilization is progressing. If we were trying to solve physics with machine learning in 1990s, it was a very possible problem. In 2025, an undergraduate student can do this, right?
With these really expensive projects, how do you see the human civilization progressing, and how is it meaningful to you?
Yeah. I mean, humans, the one of the main, it's hard to say what is the purpose of being humans on Earth. But one of the things that we can be very proud as a species is the generational knowledge we have built about the universe. And everywhere the humans move, whether they decide to move to Mars, whether they decide to go inside a wormhole and go to a different planet, the the inherent curiosity about our surroundings and the fundamental nature of it is not going to change. The question is, what is the science unique you can do with this kind of technologies that we are building? We're not going to the moon to go detect gravitational waves. We're going moon there as a step to go to Mars. It's a large moon to Mars program. However, while you are at the moon, is there a unique science you can do? Is there a unique science you can do at the International Space Station? Yes. There is a very nice neutron star imager in the International Space Station. Did we go and build International Space Station to have a neutron star experiment? No. But while we are there, we did a lot of biological experiments. We did a lot of we learned a lot about how to stay in space for this long, and in the process, we learned something about fundamental physics experiments. So you have to think of science and especially physics experiment in light of many other things that are happening. We are taking the human civilization, the human spirit of discovery further by doing experiments as are ambitious as this, as Leela is.
How do you see your project, the Lunar Initiative project, in next 5 years and 10 years?
Yeah, so in 5 years, I'm very convinced we are going to have a payload on the surface of the moon, and we are going to make some of the initial measurements that will guide us what can be done if we had also astronauts with a large lunar terrain vehicle that can travel 30-40 kilometers. What are the science that they can do? And so in the 10 year, we have this sort of a 10-year vision map that from where the current generation of landers are to where something like a starship lands on the moon, the things that we can achieve.
Wow, that's very ambitious, but also very inspiring to see you come here and achieve all these things, and to have all these really grand ideas that is going to advance our understanding of gravity and the fundamental nature of reality itself. Do you have anything to say to all the viewers or all the young physicists and students who want to pursue physics or astrophysics or any other science?
I mean, one general advice I would give is that you have to be in this for a long haul. You cannot have validation as a way to decide, how further you want to go. You have to be ready for many rejections, for many setbacks, and still not leave. I mean, that is a reality of our field, and that is something that really builds us for a long term scientist. And second, I'm very glad that Anish is doing this amazing podcast. So I look forward to listening to more of this conversation with my colleagues, with other professors. And yeah, and good luck for your next step of academic life.
Thank you, Dr. Zani.
Thank you.